Okay, so let's continue our discussion on the analysis of free fall motion. Okay, so in the first example, we learned that in downward motion, the initial velocity or v sub 1, okay, of a falling body is considered to be 0. So we assume that the object is released from rest. Okay, and since acceleration due to gravity is directed downward, we use the negative value, okay, or we use a negative sign. So it's going to be negative 9.8 meter per second square. Okay, also remember that we use the equations since free fall is an example of a uniformly accelerated motion. So we use the equations for uniformly accelerated motion when we solve problems in free fall. Okay, let me just reiterate that those equations are, okay, t is equal to v sub 2 minus v sub 1 all over g. Okay, distance or d is equal to, or displacement is equal to d equals v sub 1 times t plus gt squared all over 2. And then another equation is d equals v sub 2 squared minus v sub 1 squared all over 2 times g. Okay, so you can derive these equations to get other equations for v sub 2 or final velocity and v sub 1, or even an equation for time. Okay, you might also encounter some textbooks or some references that use different symbols. Okay, other references use S for displacement or for distance. Okay, and then instead of v sub 2 and v sub 1, you will see other references using v sub f and v sub I. Okay, but they're actually the same. Okay, so let's have this as our second example. So in the second example, let me read the problem. To start the football game, a referee tosses a coin to determine who kicks off first. So for letter A, how high will the coin reach if it is tossed with an initial speed or initial velocity of 5 meters per second? And then letter B, how long will it take the coin to return to its release point? Okay, before we solve this problem, kindly take note that this is already an example of free fall wherein the object is in upward motion. And in an upward motion, so if this is our object, okay, not unlike in downward motion wherein our v sub I is 0, this time we are given an initial velocity. Okay, otherwise the object will not be moving upward if it's not given an initial velocity. However, as it moves up, since it is moving away from the pull of gravity, the object will experience a decrease, okay, in its speed or velocity. Okay, it will decelerate until such a time that when the object reaches its maximum height, the maximum height is the highest point that the object can reach. Okay, so when it reaches its maximum height, its final velocity will become 0. Okay, and when that time comes, the object will now fall down. And as it falls down, that final velocity will now be considered as its initial velocity. And as it moves downward, instead of having a decrease in the value for its velocity, it will now experience an increase in velocity. Okay, it will increase its velocity because gravity is pulling it down. Okay, the object will also be accelerating. Okay, and then as it accelerates, as it reaches the point where it is released, its final velocity will be at its maximum. Okay, also take note that in motions like this, provided that the object is released, okay, from the same height, and when it reaches that same that same release point, Okay, the motion will always follow time symmetry. Okay, and what is that time symmetry? Time symmetry simply tells us that the time for the object to move upward is the same as the time for the object to move downward. Okay, so they will be equal. At the same time, the initial velocity when it was released would also be the same as the final velocity when it falls down. Okay, again, this is if the object is released from the, or if the release point, okay, and the catching point is the same. Okay, yun. So let's apply this in the example problem. Example problem, we are going to determine first, letter A, how high will the coin reach if it is tossed with an initial speed of 5.0 meter per second. So let's take note of our given. Okay, of course, our G is still going to be negative 9.8 meter per second square. Even if the motion is upward, G is always downward. Okay, and then we have here 5.0 meter per second. That is our V sub 1. Okay, there. And then we're going to determine how high. So that's going to be our D. Okay, so assuming that the object reaches, of course, the object should reach the maximum height because it's how high. So our final velocity here is 0. This is for letter A. Okay, so from the set of formula or from the set of equations that I have shown you, to be able to get the distance traveled, okay, or the height, we are going to use the third equation, which is D equals V sub 2 squared minus V sub 1 squared all over 2 times G. Okay, there. However, we can again shorten the formula. We know that V sub 2 is 0 and 0 squared will still be 0. So let's just remove it. Okay, so that the formula will simply become, oops. Okay, so that the formula will simply become distance equals minus V sub 1 squared all over 2 times G. Okay? Yun. So let's now substitute our given. Okay? We know that our V sub 1 is 5 and we have here the minus sign. So let's write the minus sign. So we have minus, or it will become negative now, 5.0 meter per second open and close quantity squared. Okay. And then 2 multiplied by negative 9.8 meter per second square. Okay? Yun. 5 square is 25. We square the number, so we also have to square the unit. You have meter square per second square. Why did I not include the minus sign when I square? It's because the minus sign is actually part of the equation. If you would remember, this is supposed to be 0 minus V sub 1. We just removed V sub 2, kaya naiwan pa rin. Ano? That's why minus V sub 1 is still left on the equation. Okay? The minus sign is not the sign of the number. Okay? 5 here is positive because it is thrown upward. Okay? And also, it's a value for speed. Oh, there. So we have 5 meter per second open and close quantity squared. So that's negative 25 or 25 meters square per second square. And then you have 2 multiplied by negative 19.6, negative 9.8, sorry. So you will have negative 19.6 meter per second square. Okay, let's now cancel out the units. You have here square and meter, and then you have per second square and per second square. Okay, there. So now, if we divide 25 by 19.6, we would have let's express this in 4 significant figures. We would have 1.2755 or 1.276. Okay, our unit will now become meter. So this is negative and negative. Our answer is supposed to be positive. There. Okay, so the maximum height reached by the coin is 1.276 meters. Now, for letter B. For letter B, you are asked how long will it take the coin to reach or to return to its release point. Okay, let's rewrite our given. We have solved letter A already, so we will use that as part of our given. We have 1.276. Okay, I will be writing here D max so that we would know that this is the maximum height reached. Okay, our G is still negative 9.8 meter per second square. Okay, for us to determine how long the coin or how long will it take the coin to return to its release point, we can consider one type of motion. We can consider the upward motion of the coin. Okay, so we can use the initial velocity when it was released upward or when it was tossed upward. So that is 5.0 meter per second, and the final velocity when it reaches the maximum height as 0. Okay, so that we can calculate for the time. Remember that in the previous slides, we mentioned that the time to go up is also the time or equal to the time to go down. Okay, there now. So let's use the first equation. So we use time is equal to v sub 2 minus v sub 1 all over g. Okay, our v sub 2 is 0. So let's write it as 0. Okay, and then we can do the substitution. Let's substitute our given. Okay, so we have now minus v sub 1, which is 5.0 meter per second, all over our g, which is negative 9.8 meter per second square. Okay, so let's cancel meter and meter, seconds and seconds squared. And if we divide 5 by 9.8, we would be given 0.51. We have 0.51 or 5102 seconds. Okay, we express it in 4 significant figures. This 0.5102 seconds is actually the time that it took the object to go up. Okay, if we want to know the time for the coin to return to its release point, we need to get the total time. And how are we going to get that? Okay, we know that the time to go up, okay, from here, we know that the time to go up is equal to the time to go down. So for us to be able to get the total time, we can just simply multiply this by 2. Okay. So let's multiply it by 2. So you have 0.5102 seconds. Okay, multiplied by 2. And our time now will become 1.020 seconds. Okay, there. So this is the total time. Okay, so in the next video, we'll have the last example for free fall.